for 30 minutes. I don't want to go over 30. I'm going to see where I am then. I'm recording, and somebody take really good notes in case the recorder just decides to poop out on us, because sometimes it's like, no, I will not save. It's really weird like that. So, he's just not feeling well. We can write him a get well thank you card. I mean, not thank you card. Get well card.
Already recorded.
Okay, what's up?
It's already recorded.
Yeah.
He knows I plan.
I'll edit out the first. I'll edit out the first. Okay, so on your desk you have your outline, and hopefully that, I know there's a lot of information sometimes given on those study guides because they assume you already have some background. You actually should have a little background because you took honors chemistry, but some different schools do different things, different states do different things. So have that outline out because you can always add notes to it, and if you've already have it written down, then don't write it again unless you want to. I'm that person, I would write it again, but it's up to you. So pretty much we're now to the point where we're starting to pull things together. Yes, look at this lovely soup here. So we're starting to pull together thermodynamics, Gibbs free energy, a little bit of kinetics, a little bit of stoichiometry, and now we're hitting equilibrium. Okay, so this is kind of an accumulation unit where you start to pull together lots of little things. And I'll try to tell you, like, deliberately the things that should come together, the things that should make sense. So this is me trying to do that at the very beginning, and then I'm going to follow up at the end. Okay, so thermodynamics, we've always talked about things being spontaneous or non-spontaneous, thermodynamically favorable or unfavorable. So we're pretty much saying, is this reaction going to happen without any intervention? What value would tell you if that reaction would happen without intervention? Right, delta G is going to tell us it's going to happen spontaneously. Value of delta G, that means it's thermodynamically favorable, is negative. Right. So pretty much just saying, is it going to happen, yes or no? Or is it going to happen without intervention? It can happen even if you heat it up, of course. And then the two driving forces of reaction that determine delta G are what and what? Right. The favorable conditions for delta H and delta S are exothermic, negative, and positive, increasing disorder. Okay, that is those two favorable conditions allows for delta G to be negative, which means it's an exergonic reaction, and the free energy of the reaction is going out to the universe, and everyone wants to satisfy the universe. That is the person I'm going to be friends with. Okay, so kinetics. This one's going to be basically telling us how fast is this reaction going? How many steps does it take? We're assuming it happens. Okay, we are assuming that the delta G is negative, that maybe these conditions are true, maybe, but it's also dependent upon the temperature. So we're pretty much saying how fast does it happen, or if it happens, does it happen at like the speed of light or opposite of speed of light, whatever speed of light. Okay, so that's going to be the rate of the reaction is all related back to little k. I'm trying to write little k, because little k is very different than big K that we're going to do in equilibrium. Okay, it's little small k is the kinetics k. Big K is equilibrium K. All right, so how fast does it go? What factors can affect it? We know the factors that affect reactions. Collision theory, surface area, increasing temperature, decreasing space, increasing concentration, things like that. Equilibrium kind of pulls together both of these. We're trying to see if a reaction happens, how far does it go towards the products? How many products are made relative to the amount of reactants that are left? Or does it go to completion, 100% of products made, zero amount of reactants left? So now we're kind of getting to the middle of, we might know how fast it goes, but how far does it go? Or we might know it actually occurs, but how far does it go? Stuff like that. And then based on the fact that we know how far it goes, how far into completion it goes, we can determine the relative amount, so this is concentration of products and reactants are made or remaining at equilibrium. So we're trying to kind of pulling together all these things now. So let's get started. Where's my little clicky clicky? We're going to do physical equilibrium again with states, unit 10, I think. So we're not going to hit this real hard, but we've talked about physical equilibrium before, and I just have a quick example. It's basically when you're at phase change. Phase change is physical equilibrium. So from liquid to gas, this can happen at what temperature for water? Right? This is very temperature specific. It's at 100 degrees Celsius. And if you contain this in my water molecules, they're having a good time. If you contain this in a closed container, okay, this closed container thing is a specific characteristic of the equilibrium reactions. It's very, very important, because if you don't have a closed container, anything that you make that is gaseous will leave. Okay, and that's gonna that's related to Le Chatelier's principle. Le Chat, shift left, shift right. Do you remember Le Chat's shift left, shift right? Okay. If you don't, it's cool. We're not going to do that for a couple days. But if you open up your container, stuff leaves. And then you are actually affecting equilibrium by accident. So we have to have a closed container. And basically, some of the gas, the water here, is going to gaseous form. I'm drawing on the outside because you can't see the inside, but it's on the inside of the stove here, or this thing. It's called a pot. There we go. Okay, so it's on the inside of that pot there. So some of the liquid water is going to gas, but then some of the gas that can't escape, it actually can come back together with other gas particles and then recondense. So we have gas going to liquid, liquid going to gas at the same time. When it is at boiling, we say that the rate of the forward reaction equals the rate of the reverse reaction, which would mean the rate of, what's that process called? Liquid to gas. Vaporization or evaporation is equal to the rate of condensation. So that's basically all physical equilibrium is, but it's a good intro because this is something you're like, duh, I've been familiar with this since like 3rd grade. So this is something you can really it's more tangible to you. And then this is just vapor pressure is established. That's just a side note. What causes pressure? All right, collisions with the container walls, right? So if I have vapor pressure, what's causing the pressure? Water vapor, right? The gaseous state of water. So vapor pressure is going to be established at a specific temperature, which is something that we'll kind of hit more later with state changes and phases, but it's just very temperature dependent. Everything is temperature dependent. Temperature changes a lot of stuff because it changes the energy. Second example is a similar one. It's still phase change, kind of, but it's a dissolving phase change. So we're going from solid to aqueous. And this is, some people say a phase change, some people say a chemical change. Technically, chemical changes are supposedly unreversible, not reversible. Once you combust some ethane, you're not about to take that carbon dioxide and water and go, okay guys, let's make some ethane again. It's really hard to go back. But can you go back here? Right, you can evaporate the water out, it will recrystallize into the solid form. So that's why some people are like, oh no, it's a chemical change, because it looks like it's a chemical rearrangement, but it's really not. It's more phase change than chemical change. Anyway, the rate of dissolving equals the rate of what? What's reverse? Solidification, I'll go with that. Or precipitation, you could say. It's forming a solid precipitate from 2 liquid aqueous solutions. So in this case, we're still dealing with rate of forward equals rate of reverse. Rate, on the other hand, well, we know what rate is. We know rate is K times concentration of one of the reactants, K forward. I'm just going to go put forward because that's the forward reaction in this case, equals the rate of the reverse reaction, which is the rate, K of reverse times reactant B, because I'm going to call these guys over here reactants B. It's just, are you talking about going forward or going backwards when you're referring to reactants? So these two things, these are already familiar to you. But now we're actually going to be using the rates in a different way. So, first I'm going to talk about going to completion, then we'll talk about going to non-completion. So if a reaction goes to completion, you draw a arrow that's just straight, no reversible, just completion. 100% of the reactants go to products, so 100% of products remain at the end of the reaction, and 0% of reactants remain at the end of the reaction. So far, so good? Cool. So we generally ignore reversible reactions when we're in baby chemistry, because it's a lot to take on, and you're like, what, does it go in reverse? You know, it's something that you just need to kind of get your toes wet with the completion reactions first, and then we start talking, oh, they can re-react and go back to reactants. So most of reactions are reversible. Okay, newsflash, most of them are not going to completion. A lot of times they are reversible. We don't scare people though away in baby chemistry, because sometimes you're like, I have too many things to remember. So when it's reversible though, you write the double-headed arrow like you've seen a lot. And usually I just write it like this, little half arrows like that. It's easy to do that. So let's talk really briefly about my example down here. If you started off with 0.07 moles of nitrogen dioxide, that means before the reaction you're starting off with 0.0700 moles. And if I tell you that at equilibrium you have, I'm just going to show you this one example first. At equilibrium, you are going to have form 0.0292 moles of the dinitrogen or tetroxide at equilibrium is going to be after the reaction has occurred. So I'm going to try to set up like a BDA table first. So this number over here, 0.0292 moles of dinitrogen tetroxide is made, and then this is how much is left. So you're forming this 0.0116 moles. All right, so what was the change, or what would you do to find the change? You subtract what? Great, let me see if I can move. I can't move this. I can't move this. Haha. All right, so I would find the differences are during the reaction by just taking, sorry, you start off with 0 of that if it doesn't tell you start off with anything. You take what you started with minus what you ended with. So, do I have that number? Will somebody calculate that? It's like 0.05. 0.0584. Okay. All right. Now that change though is equivalent to 2x. And I call it 2x because I have a ratio of 2 to 1 for my reactants to products. So this reactant is decomposing or reacting twice as fast as the products are made. So this is equivalent to 2x. And then what's x? That divided by 2. Okay, so x is equal to 0.0282.
What did you know?
92. Thank you. 5, 4. Oh yeah, sorry. All right. So that's how much x is because you have a quantity of 2 times that number being subtracted here, but you're making products, so you're adding it here. Because you can't destroy matter, it has to be conserved, so whatever you react, you have to, or when you react something, you have to add something to the product side. But this is not reacted in the same ratio. This is not made in the same ratio. You only make 1x here. Well, we know what x is because we just mathematically found it out to be 0.0292. Guess what? That's what we got. So that kind of further verifies your math works out there. So far, this whole year we've been doing before, during, after tables. Essentially, equilibrium has a similar table. It's called ICE table, initial change in equilibrium. It's just because when we say after a reaction, we're saying that reaction has gone to completion. After the reaction is occurred, it's not going to go back, it's not going to change, we're just stopping it after. But now to be a little bit more correct in the way we talk about it, we say initial change in equilibrium, because at equilibrium, it can still change. We can still have reactions occurring. Depends on what kind of conditions you change them. So instead of calling it a BDA table, pretty much from now on, for at least another month, I'd say, we're going to call it an ICE table. And then if you got to the very last page in the reading, it was page 7, it was a rice table. Makes me laugh every time. I can't stand to call it rice there. It's because rice refers to reaction, and I'm like, you better be writing your reaction. I'm not calling it a rice table. It's an ICE table. I never learned it as a rice table, so I just laugh when I say rice. Rice. So it's the same thing now. If I had done another example, you would see this a similar ending point, and then we would use that information to find the equilibrium value, which we're going to do in just a second. Okay, so 2 types of equilibrium, heterogeneous and homogeneous, pretty self-explanatory. One is very, very easy. The way you write it is all gaseous. One is going to have some solids, some aqueous, some liquids, and some gases, probably all intermingling together. It's just these heterogeneous ones are a little bit more tricky because they have some exceptions to how you write their equilibrium expressions and what numbers are truly important. Let's start with here. How long have I been talking? Like 5 minutes? Let's see here. So these are generally going to be used in problems called KSP problems or solubility product. Problems, and the SP here for KSP is what SP stands for, solubility product. That's something you'll read about 4 days, I'd say. So in this unit, we're going to talk about KCs, KPs, KEQs, and KSPs. And they're just different, they're all equilibrium, same exact thing, just from different types of reactions. But who cares? As long as you know how to do 1K, you can do any K. I can give you dinosaurs and ponies. You'll be fine. It really doesn't matter. Once you learn K, you can do K for the rest of your life. Now, this right here is an example of it because we can see that we have solid, solid, and gas. You can have liquid or aqueous and they're intermingling as well. Usually with gaseous equilibrium, you're going to be using KP because KP stands for K pressure. KP, this is a capital K. I really try to show that I have capital Ks for slow Ks. KP is going to use the partial pressures of gases. So don't be scared when you see the partial pressure of blah, blah, blah is 1 atmosphere, 2 atmospheres, 0.01 atmospheres, whatever. Just call it a concentration because gases don't, it's hard to contain gases and count how many little atoms they have and how many moles they have over so many liters. So we generally just say, okay, I know the pressure of it, and that's related to their number of particles because the pressure is caused by particle collision with the container wall. So concentration and partial pressure are kind of equivalent between the two different types of reactants. So when we use Ks, when we use pressures, we usually go like pressure of 1, pressure of 2, over pressure of 40, whatever I'm talking about. So it's just the big P like that just means partial pressure. Aqueous is going to usually use molarity as its concentration because you can normally find that out. We're going to talk about acid and base next unit. They use different Ks, Ka and Kb for acid and base. And at the end of this unit, we're going to use KSPs to talk about precipitates and amount of a precipitate that actually does dissolve, because not all the precipitate actually is precipitating out. Some of the ions still remain in solution. Okay, so for your equilibrium graphs, I really was hoping we'd get there, but it's okay, we didn't. You would see a graph, and some of you guys may have seen on your reading and from your data, you generally start off with how many products. Reactant B, graduated cylinder B was your product. How much do you start off with? Nothing, okay? So this graph is going to be concentration on this side and time down here. Generally, you start off with 0 of products. I'm going to go red is product, okay? Over time, what happens with products? Right, generally they increase. And I'm just going to draw one example of how this increases. But over time, as you guys saw with your, I think you guys were like 12 or 13, what happened to your amount of product made? It levels off, right? Because as you made product, you were also going backwards and making a reactant, which was graduated cylinder A, except for some of us. So you can see that it actually levels off. So the products made starts to level off, right? Well, who's making the products? Reactants. Generally, you're going to start off with a higher amount of reactants generally. And as the reactants are used, that's why your products increase. As reactants are used, the products increase. As reactants are used, the product increases. As reactants are used, the product increases, and so on. But whenever reactants start to also level out, the products level out. Okay, so you'll see graphs like this, and you'll see another one similar to this I'll show you in a second. Equilibrium's definition is when the rate of the forward equals the rate of the reverse. So you have your two straws and you're going from A to B and B to A, and you move the equal amount of reactants to products. Did anything really change? No. Okay, so you were dynamically moving things back and forth and back and forth and back and forth, right? But was the volume really changing that much? No. At that point, the rate of the forward moving from reactant A to B and the rate of the reverse from B to A, they're equal. Their rates are equal. You're moving equal concentrations to and from, which is the point of equilibrium. So what is equal at equilibrium? Not all the time. What is at 100% of the time, no choice, no questions asked for, is always equal at equilibrium. The rates, thank you. Okay, so not all the times are the reactant concentrations and the product concentrations going to be the same. In your lab it was, because you guys stopped at like 12.5 and 12.5 about. But look at my graph here. Where are the rates? Let me extend my graph here. You'll see at time blue line here, okay? You'll see that right there, they start to go stagnant, which means the rates of the forward and the rates of the reverse are equal. That means the concentration of the products are no longer changing. The concentration of the reactants are no longer changing. But could they actually still be exchanging with each other? Yeah, it's just net, no change. So no net change of concentration of reactants or products. But notice that this product is way higher than this reactant. So even though, yeah, we have hit equilibrium at this time, the concentrations are not the same. That is the biggest misconception, is when you say equal, you're like, oh, everything's equal, everything's hunky-dory. Don't let yourself fall into that trap. Sometimes they're equal, but it's very rare. Okay, so at equilibrium, concentrations are constant. They still can be frantically moving back and forth, though. Looking at this reaction here, what is favored, formation of products or formation of reactants based on the graph? Right, formation of products. Products are favored, and I'll tell you a hint now. Anything that's on top is going to be the one that's favored because you have a higher concentration of it at equilibrium, which means that that reaction favors the formation of the products because maybe the products are more stable, and so the reaction overall has less kinetic energy, potential energy built up into it. So the products are favored here. This K, equilibrium K value, is greater than 1. I'll explain that again in a second, but I just want to go ahead and make that point now. Oh, I don't know where I put the rest of my stuff. I may have it on the next slide. Well, I'll go over this one. Yeah, I'll go over this one. Okay, so here's the second graph, and this is the formation of ammonia. I'm sure you can write the formation of ammonia from like your thermochemical equations, formation of ammonia from its elements. You'll be asked to use that a lot. Okay, so that's pretty easy. Now you're starting off with reactant H. I have to sneeze. Reactant N2. And you're making
Orange bananas, red pickles, and green.
Alright, it went away. Was that supposed to make me sneeze?
What?
Was that supposed to make me sneeze? I was supposed to distract me. Okay, cool.
I did. Good job.
Okay, so you can see, what do you see that's different about the rate of disappearance of H versus N? So hydrogen versus nitrogen. Who's faster? Hydrogen's 3.5 times faster than nitrogen is disappearing. Because, oh no, not half. I'm sorry, I was going with ammonia. It's 3 times faster than nitrogen. So you can figure that out from a graph just like you were able to with your like zero order rates of reactions. Nitrogen or ammonia is forming twice as fast as nitrogen is reacting. Yes? See the difference in slopes. When do they meet equilibrium? When they what? Okay, when they're static. But what is true about equilibrium? The rate of formation of ammonia is equal to the rate of formation of the reactants. Okay, cool. So you'll see that this graph looks a little different. The product, in this case, is halfway favored because the reactant hydrogen is still above it. So it's very hard to find, to determine the K value from something like this. You'd actually have to plug it in and calculate it. So it doesn't always matter what you begin with. So this is a similar, we have a different reaction. We have hydrogen and iodine makes hydrogen iodide, and then vice versa going backwards. I can start off with the green right here, which is reactant. So I'm starting off with reactant, and I'm starting off with no product, which is kind of a given. And you'll see that the equilibrium state still yields higher amounts of products. And then I can go in reverse. I can do the reverse reaction, so I can start with my products and make my reactants. So HI is technically my product. You know, I've written it backwards here. Generally, don't write it backwards because it kind of messes you up. You're like, is this a reactant or product now? In our general reaction, H2 plus I2 yields 2HI. The HI is our product. So if I give you a lot of products, they're going to then react, and the reactants are going to form. But it doesn't matter what I start with. You see that it ends at the same place. Still, products are favored. Still, they're going to end at exactly whatever this concentration here is. It doesn't matter if I start with something really, really high up here or really, really low down here. It's always going to stop at the same. The equilibrium position, the number of the concentrations of products reactants is always going to be a standard at a specific temperature. You can't change it. It's always going to end up that way. Just like, let me give you an example. I'll think of one. Okay, so here's some more characteristics of equilibrium. And these are just like factoids that unfortunately you have to know. And some of this is from the reading as well. So there usually are always at equilibrium. There's always reactants and products left. Always. Never zero of anything. You're going to say the terms no net change in a lot of your descriptive answers. Because equilibrium, technically, there's no net change, but it can still be dynamic. also dynamic on the molecular level, because the molecules can still be technically reacting, but if they react in equal rates, you'll never know, like from a graphic standpoint. Almost never will you see that product's concentration equals the reactant concentration. Almost never. That graph would have to look something like this. They would have to meet in the middle like that, and it's very rare usually to see that. Sometimes the graph will look like this. So we've seen one where the reactants and product lines cross. That means that the products, if they go on top, then they are favored. We've seen one where they may be touched, which would represent equal concentrations, which is rare. And then you'll see one maybe like this sometimes. Well, in this example, are the reactants or are the products favored? Right, because you usually start with reactants, so you're starting with the reactants there. The reactants are favored, the products are not favored because they're lower. Just on a, one where they don't cross, they just kind of level out. And then sometimes to show with an arrow which side is favored, it'll be written like, okay, here's where no side is favored, equal arrows. If the products are favored, so it's pointing towards the product side, just saying, I'm favored, this side is more, it's happening faster than the other side or more often. Or, and these are arrows, the other way. The reactants are favored. These are just arrows. Just put, it's like a bigger arrow pointing towards the side that's favored. Okay, so this would be K is equal to 1. K is greater than 1 when the products are favored. K is less than 1 when the reactants are favored. Good to go? See, señorita? Senora no? Senora no? Oh, yeah, okay. All right, so, okay, now it's going to talk about the rate laws and how this applies to kinetics and equilibrium now. So the definition of equilibrium is the rates of the forward equal to the rates of the reverse. Well, if the rates of the forward are equal to the rates of the reverse, then these two things should be equal, right? Yes? All right, that means these two things should be equal, yes? Okay, they should be if the rates are equal, and this equals that, and all these things are all equal to each other. So then I'm going to set this equal to this. I'm going to write that down here. And you can see my reaction is just A yields B. So Kf, and this is little k, times concentration of A is equal to Kr, which just means the reverse reaction, times concentration of B. I want to set this up so I have the K's on one side and the concentrations on the other side. So I'm going to divide by A here. I'm going to divide by Kr over here, so the reverse. These cancel here, these cancel here. Now I have two K's on one side, Kf over Kr is equal to concentration of B over concentration of A. All right, there's something I'm not telling you. It's the equilibrium constant, big K, equals the ratio of the forward rate constant over the reverse rate constant. So pretty much what I'm saying is this equals K EQ, or the equilibrium constant K. I'm saying I didn't tell you that because I don't want you to think about ratios. The definition of the KEQ, the equilibrium constant, is the ratio of the forward rate constant over the reverse rate constant. So the forward rate constant over the reverse rate constant. But I usually never, ever write these things because they confuse people, because that's like kinetics and we're in equilibrium. So generally, you only see this equation. KEQ, so this is big K, KEQ is equal to concentration products over concentration reactants. That's its products. It's ugly. Concentration of products over concentration of reactants. So that's just some background on how we even get to big K, to equilibrium constant K. But you've seen this before. You've seen equilibrium constant equals products of reactants. Okay? Now you're to the point where you're like, okay, I know what we're talking about. I've seen this. That's how we get there, but half the time nobody cares how we get there. We're just like, just tell us the information. Let's move on. So this is the point where now we're moving on. Let's do some more deriving of K. So the equilibrium constant K comes from the law of mass action. I have no idea why it's called the law of mass action. Mass action. Mass action. This is something I don't really know. But this is the definition of the law of mass action. Essentially, a reaction, we'll leave that up there, keep my copy of that down. A reaction's coefficients are used to make exponents. You just have to put the product's concentration to raise to its own exponent over the reactant concentration raised to its own exponent. It's called the law of mass action. I didn't know it was called the law of mass action, so I started teaching you chemistry. I just knew products and reactants. So it's just one of those things that it stays with you if you really focus on it, but there's a couple of multiple choice questions that'll say the law of mass action, you just have to know what it means when it says that. So use the molecularity, so the coefficients, to determine the constants expression. So this guy right here, K, in this case this is Kc, this is called the equilibrium constant. This big honking thing here is called the equilibrium expression. So let's say you write the equilibrium constant, you write Kc or Ke, or sorry, Kp, Keq, they're all the same K, it's just talking about different types of reactions. But if I say write the equilibrium expression, you write products blah 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 over reactants blah blah blah. And you'll notice that, you know, I took my little c right here, this c which is a coefficient, I raised it to the exponent of that. My little lowercase d here, raised it to that exponent, so there's my products, over my little a, which is the exponent for the reactant A, and the little b, which is the exponent of the reactant B. If I wanted to do the same exact thing but for Kp, I would write pressure of C raised to the C power times pressure of D raised to the D power over pressure of A raised to the A power times pressure of B to the B power. So still just products of reactants, it's just using partial pressures versus molarities. We've talked a little bit about what it means in terms of the size of the value, that it's greater than 1, less than 1, but here's a little bit more. So it's basically, you can see it's a ratio of products concentration over reactant concentration. So earlier I was making the note that when K is greater than 1, products are favored, right? Well, how does that mathematically work? If it's the ratio of product concentration over reactant concentration, K being greater than 1 just means you have a larger number on top than a number on the bottom, right? So the numerator is greater than the denominator. Well, that makes sense because the numerator is the products. So if the numerator is larger, the products are larger, so therefore the products are favored. If you have something where you have K is less than 1, the reactants are favored. How does that work out mathematically? Right, the denominator is going to be larger, which is the reactants concentrations, therefore it's favored. So whichever one is greater in concentration or greater in partial pressure, that's the one that's favored. Because they just have more of them at equilibrium, which means they're more stable. So it tells you which side is favored. It is independent. So this big K, it's known, you're supposed to say it's independent of little k, the rate constant. So, because you can't look at one rate constant, like the rate of the forward or the rate of the reverse, you have to look at the ratio of them. So you can't look at just one and say, oh, this reaction happens really fast because it's got a really large rate constant. It tells me, I don't know about the equilibrium constant. You can't look at the k value of one thing and say, oh, I know which side is favored. It doesn't matter how fast this reaction goes. It doesn't matter how slow this reaction goes. We care about, at equilibrium, are the products in higher quantity or the reactants in higher quantity? Because I can still go at the speed of light, and maybe something's happening different in the reverse direction. You cannot relate the two. You have to look at them as a ratio. And hopefully we will never have to do that. Okay, let's do, oh, I forgot to tell you back here. So under your equilibrium constant, let's say that this product over here was a solid. You are not allowed to include solids in the equilibrium expression because solid pressures, first of all, do solids have pressures? No, so it would not affect the pressures. There would be no partial pressure for it. Do solids have a molarity? No, they don't have a certain amount in the liter of water solution. What? That's not the same. So you cannot have a molarity for a solid. Can you have water dissolved in water? No. Okay, it's a pure liquid. You can't have so many moles of water and so many liters of a water in water solution. Like, it doesn't work. Okay. So if you had, for example, solid for D and liquid B, they would not be included in the equilibrium expression. You just wouldn't write them. So never, never, never should you include pure liquids or pure solids. That would be listed as an S or an L in your PC. And that's what this says. Never have, they all have constant densities or constant concentrations if you can assign a concentration to it. Therefore, never include pure liquids or pure solids. They're technically already embedded in the rate, in the equilibrium constant. So we just pretend they're just irrelevant, but they're kind of embedded already. So we never worry about it. All right, so let's do this one. So you guys tell me, what is the expression for the first reaction? Okay. Concentration of carbon dioxide. Nothing else, right? Ignore. This has a coefficient of 1, so I usually try to put my coefficients as exponents in case somebody forgets to do that in the end. Okay, cool. So that one's easy. Next one. Concentration of NH2 or NH3. What? Cool. It's like a mantra. Okay, so let me do one more. Yeah.
The last one.
Do the last one? Okay. Go for it. This is H2O gas, right? Because it's cool to include. What's that called?
Sodium bicarbonate.
Thank you. Also known as baking soda?
Wanted like another.
No. Or sodium hydrogen carbonate. Sodium hydrogen carbonate, whatever. That's baking soda. Okay, so you raised it to the second power. You excluded this solid. It doesn't have a concentration. You could easily, I've been putting KQ. KQ is kind of like the cover your butt, like I know what I'm doing, because you don't have to specify is its pressure, if it's concentration, if it's acid, if it's base, if it's a KSB. It kind of like just summarizes, I'm just talking about equilibrium constants. I don't care what type right now. So that's why you'll see KQ a lot, but if we're talking about specific pressures, you'd be putting pressure here, here, and here, not brackets between concentration. So we're going to stop here. I'm going to see if you guys can do the textbook, some of the textbook problems. You guys can try to attempt them. We'll finish these up tomorrow. We have like eight more slides maybe. Where did I put your homework? I have it on the website. But for the last 15 minutes of class, what I'd like to do is we're going to get our tests back, review some of them, go sit in the back and you can watch videos from last week. Okay, bye. And so I just want to basically let you have some time to talk to me because I can't tutor today or tomorrow because I have meetings. People like to meet with me every possible day. So you're going to have some time with me in class. These tests will not leave my classroom. Talk to me about this. Make all the corrections that you possibly can, and I will give you back some points. I can't promise. I was going to do half credit back. That is kind of my goal, but we'll see how well this goes, okay? Because really what I need you to know is I need you to know this information. If you have some misconceptions, we just have to correct them. It's not a big deal. It's just that I can't let this can't happen more than a couple of times. But then I have to reteach things. If I need to teach things, then I need you guys to be a little vocal about it. If the majority of the class is like, we don't get it, If I need to spend more time, this is fast. I think right now we have about 20 days set aside to review at the end of the year, and trust me, you'll need it because you'll forget stuff that we did like now in April. You in library or here, right here? We just, oh, okay. Look at the homework online, okay? So if you need me to help you now, I'm here. If not, we'll do some of this again tomorrow. If you want to work with a friend, work with a friend. But I added in your study evidence already. There were 2 questions on multiple choice that dealt with Arrhenius' equation that I'm probably going to go back and give you some credit back for, because at this point I wish I had provided you with Arrhenius' equation, and I can't do that at this point. But we'll take the test. And that's a hard equation to remember. So you guys can look over this, but I'm going to just talk out loud about a couple things. If you want to listen, you listen. If you don't want to listen, do it. If you feel like you're feeling pretty good about your score, you can check out your stuff yourself. That's cool. Let me stop recording real fast.